Thank you. So we continue from our discussion and so somebody had a question on continuous. Is that student there? Somebody had a question on.
Sir, I have one question.
Tell me.
Sir, that VLSI chip part and then the timetable scheduling and symbolic integration, how is it single agent?
Symbolic chip design, there is only one person designing the chip, no? Okay. So the person who is designing the circuit, he is the person who is making all the connections, no? Yes, sir. So there is no second person who is making the connections in parallel for any conflict. That is the problem. Same in timetable. There is one algorithm which is solving the problem. Yes, Ishan, what was your question?
Sir, this we were discussing like the how transitions are different, right? So right. You said that here it is continuous domain, so I didn't understand this.
See, each transition here is a movement of a joint, right?
Yes.
Here each transition. Now this joint can move in how many ways? It can move in X, Y, Z directions or X, theta, tau dimensions. You know, either it can move angularly or it can move. So this could move in many directions. Yeah. And because it can move in many directions, it could be continuous. But we will assume that we will only consider some degree of error and assume a finite set of sequences. Yes, Prathamesh, what was your question?
Sir, is this state tables are similar like we design in digital logic design?
The infinite state machines are similar state tables, yes.
Okay.
But here the graphs are very large and it could be infinite. So now
in the morning you asked us to think about a single agent adversarial system, right?
Yes.
Sir, if we take the adversary to be the environment itself.
Yes, exactly, Macharla, Nitin, Teja. So in cases where you are trying to work or do something to a system which is considered an environment and where you don't have control over all the, if you take an action, then which state the environment will go. Maybe, for example, you press the brake of a car and it can go in, it can stop, or there is a 0.01% chance that the brake may fail, right? So that is where is the adversary. Yes.
But sir, how is this different from a robo arm?
The robo arm, if you sometimes a robo arm could be adversarial when it is when it is working in an environment, and in many cases you could consider it to be discrete also. But here I'll tell you the difference when we come to it. See, I'll tell you what is the difference. So let me show you the. So suppose this is a control plant, okay? So this is a control. Can you see the control plant picture?
Yes, sir.
So suppose this is the control plant. Now this control plant has got many variables, okay? But you are observing, so observable variables. And there are many actions that you can take on the control plant, but all actions are not under your control. So if the total set of variables is V1, V2 up to Vk, which is the set V, then the set of observable variables O is a subset of V, because you don't get to see everything. Now, whenever there is a state change by an action, similarly, there are many actions that occur. Temperature change, something happens, etc. But all actions are not under the control of the controller. So if A1 if A1, A2 up to AP, A is the set of all actions, then the controllable actions will be a subset of it. Now what happens is that when you take, so whatever you are observing, the O is actually not the actual state. You're only seeing part of the state. And when you take an action, depending on the action that has been taken, is my screen gone blank?
No, sir, it's fine.
Okay, depending on the action that has been taken, then you know what really happens is that the system has some more internal actions may happen. Therefore, because some internal actions may happen before you get a chance to do the next action, so it works like an adversary, like you said. So,
sir, I'm sorry. Are you sharing a board, sir? It's not visible from my end.
It may not be, but it is visible to the others. There may be some problem at your end. I can show a picture. I'm showing my slides.
Sir, the control plant is visible where you have written VO and
yeah, that is what I'm showing. I think he cannot see that also.
Okay, sir.
Who cannot see? Who cannot see?
So even the slides are not visible, sir. I cannot see, sir.
So that is the problem at your end, I think.
Sir, actually, even I'm unable to see the things. I think others are facing this as well.
Yes, sir. Even I'm not able to
No,
see.
I can see it. I can see it clearly.
Yes, sir, it is visible from my side.
Sir, joining again may resolve the issue.
Huh?
Sir, I guess majority of the people are unable to
Joining again may
sharing.
resolve the issue.
I can try to share again. You know what I am doing is when I'm writing on the tab, I am seeing on another computer, so I can see what is coming. So I cannot use app now. I'm very sorry. I'm writing on a tab. I'm using an MS Teams app on a tab. What else do you want me to do?
Sir, would it be possible to reshare the screen?
Yeah, that I can try again. To reshare the screen. I can stop sharing and try resharing again. But if you suddenly tell me you are using an app, please go and start using an app now. I'm using an app from my tab.
I think those who are using website, using Chrome or anything, they can.
No, I'm using a website to view, and it was coming clearly on that website.
So now it's visible, sir. Yes, sir.
Right. So what I was
yes, it's visible now, sir.
Right. Fine. So what I'm trying to say is that when you are working with a system for which all variables are not observable and all actions are not controllable, then what happens is when you take an action A, then the system reaches some state and some internal actions also take place, which is not under your control. And you reach a set of states. So while these are under your control, the first set of actions and the outcomes of those actions are under your control. The final result that you get is not in your control. And what you see is only the observable variables of the states. So this is how even in a single player, because as you said, because of the environment, it can happen.
So basically in a RoboArm, there is no defined adversary, but in a single player, we know that there is an adversary.
Yes, yes, yes.
Okay.
Now, when we come to the integration problem, Anindita Bhattacharya, you had a question.
Sir, I wanted to ask whether the control plant or the car brake problem was an example of single player adversarial.
Yes, 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 yes. Where the adversary is the environment.
Thank you, sir.
Now suppose you have the integration problem. You know, we solved x squared plus 3x cubed dx. And then we said that some rules are AND rules and some rules are OR rules. Therefore, the state space generated may be generated like this. And suppose this is a goal state, this is a goal state, and this is a goal state, suppose. And this is an AND node, this is an AND node. Therefore, here the solution is no longer a path. One solution could be a path like this. Sorry. One solution could be a path. There is one solution which is a path. Can you tell me which one? This one. Right? The red colored solution is a path because it goes through only OR nodes. Whereas another solution could be like this. So when you have AND OR graph nodes, the solution, just one path from start to goal, need not be a solution if one of the intermediate nodes is an AND node. And therefore you have to find an ANDed subgraph. And as we shall see later on, in game playing, we also consider the adversarial node in an ANDed fashion. Another kind of problems which arise here, which Professor Sudeshna Sarkar mentioned, was constraint satisfaction. Now, this is a crypt arithmetic problem on the left. Can anybody tell me what is the problem statement? Okay, by the way, Prathamesh, what is your question? Why the red? Why, sir, why red is path only? Tell me another path which can be a solution to this problem. Prathamesh.
Yes, sir.
Tell me another path which can be a solution to this problem in this graph.
Yes, sir, that is the only path.
Okay. So let us come back to this constraint satisfaction problem. In this constraint satisfaction problem, can anybody tell me what is the problem here? What is it we want to solve?
Each letter is decoded by a number from 0 to 9.
Correct. Each letter is equal to a number from 0 to 9. And we need to decipher what these numbers are so that we can decode, and they must satisfy the arithmetic operation. For example, in the whole series from 0 to 9 can be, and each character is distinct. That means that two characters cannot be mapped to the same number, same digit. So B obviously cannot be 0, right? Because B obviously cannot be 0, because what is the relationship we must have between B and Y?
Square.
Square, yeah.
Square of b.
The 10th digit of the square of b should be equal to y.
Right. So this is the problem where there are constraints which are generated by some mechanism. Similarly, you know, the scene labeling problem or the labeling problem, the face recognition problem also has a constraint satisfaction definition. One of the most well-known constraint satisfaction problems is the crossword puzzle. For example, you are given this crossword puzzle and you are given a set of words. So tell me, how would you solve? What are the constraints? What are the constraints here?
Size of the word and whether it is across or down.
Correct, correct. So one across, the third letter of one across will have to match with the first letter of two down, and the fourth letter of two down must match with the first letter of seven across. Correct. So when you have these complex constraints, it comes in scheduling, it comes in visual inspection. You are looking at an object, a 3D object. When you reconstruct 3D objects from 2D images, then you have to solve such kinds of constraint satisfaction problems. And then when you're doing such sort of face recognition, identification of parts of an object, etc., again comes constraint satisfaction, and we shall discuss constraint satisfaction in more details. Now, the state spaces, their solutions, as we have just described. The state space could be a perfect information state space. That means the actual problem space and the state space that we see is a perfect information state space, or it could be partial information. These two, both the Tower of Hanoi and the chess, are perfect information states, and the outcomes are deterministic. The outcomes are deterministic in this particular case. The outcomes could also be non-deterministic or probabilistic, as we just saw in the plant example. Then the problem could be a single player problem, or it could be a multiplayer problem. And there in multiplayer problems, it could be adversarial or it could be collaborative. Can you tell me a multiplayer adversarial problem? More than two players adversarial problem.
Carrom board?
Bridge.
Ludo.
Football. Ludo. Bridge. Now Ludo, is it deterministic or non-deterministic?
Non-deterministic because it depends on dice.
Because you have to roll the dice, so it is a non-deterministic problem. Whereas in Carrom, this strike is what? Deterministic, non-deterministic, probabilistic.
So it is still non-deterministic because it's not possible to generate the exact.
Because it may be
non-deterministic.
Yeah, and it is a continuous space, so you have to really approximate it in a more intelligent way. Bridge. Somebody said contract bridge.
So what about the perfect shot in carom? If a professional is playing a carom and the shot is supposed to be a perfect shot, then it will be a deterministic output.
No, perfect shot. See, in a probabilistic environment, like you're pushing the brake of a car, there is 95% chance it will stop. So, but you have to take into account, even the perfect player does not make perfect moves all the time in their lives. No?
Yes.
But bridge, this contract bridge, this is what? This is a perfect information game or a partial information game?
Partial.
It's a partial information game. It's a collaborative game or an adversarial game or both?
So probably both.
Both, because there are two players who have teams, and there are two teams and there are two players, and it is partial information. And where you get the information other than your own cards? From where else can you get your information?
From the
bids.
cards you have.
From the bids, So given such huge combinations of state spaces, our objective, like this contract bridge, sometimes if your partner, one side is playing, then your partner throws their cards down. So everybody sees one set of cards which is displayed. Everybody has their own set of cards, and then there is a bidding system by which you can have a guess of the other options. Now, the size of the state space, the cost of the solution, and these being meta algorithms, how to use domain specific knowledge, or which is called heuristics, is one of the key elements of search. That means the knowledge that I will use for chess, the knowledge that I will use for bridge, the knowledge that I will use in the search tree for Ludo, the knowledge that I will use in the search tree for some other problem, all will be different, and it is this knowledge dependence which is critical to making the search problem specific. So how do we integrate that knowledge? Moreover, there is this knowledge versus exploration paradigm. The more accurate your knowledge is, the less you have to explore the overall state space. So based on this, our objective is to create these algorithms, and the algorithms that we create are known as heuristic search algorithms, and that will be the focus of the next 2-3 lectures this week and next week. So now just let us do a quick recap of what we wanted to do before we move on to some other issues.
Sir, after the class, if we have any doubt,
I am there.
Okay. Means should we ask to TA?
Yeah, you can put it in the chat box. We will answer. You can. So what we are really concerned about is state space search, and just a quick recap. So the basics of the modeling is that we need to define a state or a configuration. All right. We need to define a state or a configuration, and this configuration currently in the state space modeling, we will define a state or a configuration by a set of variables. Then for every variable, we will define a domain, and then we will define the constraints among variables so as to be able to clearly define what is a valid configuration. Say in the timetable, what is a valid configuration? Say in chess, what is a valid configuration? So for each case, we'll define valid configuration. Then we'll define the state transformation rules. And there again in the moves or the state transformation rules, we have to indicate what are OR and what are AND. Then we have to define the start states and what are the goal conditions. The goal condition is checked by a function. And this defines this whole state space or implicit state graph. This implicit state graph, as we said, is huge. And the solution cost depends on the type. If it is only an OR graph, then the solution can be the length of the path. The solution can be the cost of the path, because each action may invoke a cost. For example, a robo arm may invoke a cost, which is energy. Sometimes the cost may be just one. So we will see several examples of certain costs. And then we want to incorporate heuristics, which will be our goal. And by incorporating heuristics, our objective is to explore what are the search algorithms which solve this problem well. Yes, Shubhranshu?
Sir, does the rules often give the same degree of information with respect to constraints between? So when you said that the variables could be constrained for the added configuration, wouldn't the rules or the transformation rules also kind of cover that?
Yeah, typically the transformation rules should take care to ensure that you generate valid states.
Correct. Okay.
If a state is valid, then a properly written set of transformation rules would like to generate valid states.
Yeah. Okay. Yep. Thank you, sir.
So we did this 2jug and all this stuff. So have all of you heard of the traveling salesperson problem? Who has heard of this problem? Anybody who has heard of this problem?
Yes, sir.
Oh, there are several people who have questions. Sneha, what is your question, please?
No, sir. Raise my hand.
Okay. Harsh Makwana, any question?
No, I just heard of the problem.
Okay. Neha Dalmia, Ojas Deshmukh, Suman Dev. Okay, no problem. So
because everyone had raised hands because they knew about the traveling salesman problem.
I can't hear you. Once more.
I'm sorry. Everyone had raised hands. The people who had raised hands.
Okay. So you know the traveling salesman problem, right?
Yes, sir.
So tell us, what is the traveling salesman problem?
Salesman has a salesman wants to travel to different cities, and he wants to make take a suitable route such that he doesn't travel any city twice and he returns back to the same city from where he started.
Perfect. So
more like a sir.
Yes.
Yes, sir. To just add on one more point, the minimal path that you can take to deliver or traverse a path. Yeah.
Right. So the traveling salesperson problem is to find a tour which starts from one city and returns to that city and covers every other city exactly once. Correct? So, and you are to find the minimum cost tour. Correct? So, Sneha, is that right?
Yes, sir.
So now in this problem, suppose there are 5 cities. And this cost could be the cost of the road, the cost could be the time cost, the cost could be the travel cost or whatever. At least assume there is only one cost. Smarak, you have anything to say, or Shubhranshu?
No, sir, I accidentally pressed. Sorry.
So here, can you tell me which is the shortest cost tour? What is the shortest cost tour in this example?
A, B, D, E, sir.
A, B, D, E, C, A. What is the total cost? A, B, D, E, C, A. What is the total cost?
435.
Right. The total cost is 435. So we know in this case the sequence is A, B, D, E, C, A. Total cost is 435. Can you give me a state definition? How will you define a state?
Just the node at which the agent is in.
Just the node at which, suppose I am at node C. How do I know how I have come
Okay, yes.
directly from A
List
or A
of
to B?
List of places I've already visited.
Right. List means, is it a set or a sequence?
Ordered list, yeah.
Right. So first is that I need to have an ordered sequence, x1, x2, some xk, I have reached up to xk, and a cost c. That means the cost that I have come to till now. And a state is to be valid if x1 is, any of this, it could be anything. And what is the relationship between x1 and x2?
They cannot be the same.
And
so they should be connected.
They should be connected by the state transformation rules, or the connected in the original graph.
Yeah.
Now, and what is the state transformation rule?
The node should not be visited yet, and it should be accessible by the previous node directly.
Except?
The last
You're right,
node,
but not complete.
Except the start.
Except A.
Except when you have covered every other node, you need to go back to the start. Right?
Sir?
Yes.
So the city can visit it 2 times because maybe the sum is lesser than the direct means traveling from one city to another.
So that is called the Chinese traveling salesman problem. So there is a traveling salesman tour and a traveling salesman walk. So that is another problem. The problem where you can visit a same place twice is another problem. And obviously there are cases where you could get a shorter path by traveling the same place twice. But the original problem that is defined as the traveling salesperson problem, there you are not supposed to revisit any place. But obviously there is another problem where you are allowed to revisit. All right, Chirag.
Yes, sir.
So the state transformation rule, as somebody just, yes.
Sir, I'm sorry. I could not understand how we exactly defined the states.
The state is a sequence of nodes. For example, my start state will be what? A0. Correct?
Yes, sir. Yes, sir.
And from A0, what could be my next states? A, B, how much?
100.
You got it now? A.
Yes, I got it.
120, etc. What will be the size of this state space for the traveling salesperson problem? No, in general, for n cities.
Say 2 power n.
2 power n is an upper bound. Anything better?
Sir, it would also depend on the connections within those n cities.
Suppose everybody is connected to everybody.
Sir, n factorial.
N minus 1 factorial.
N minus 1 factorial. N minus 1 factorial, it is bigger than 2 to the power n or less than 2 to the power n?
So less than 2 to the power n.
Achha?
So bigger.
You remember Stirling's approximation?
Yes, sir. Forgot.
So such state spaces are very large, and this is how state spaces are formed. And like this is the state space as in the next slide. This is the part of the state space of the traveling salesperson. Now the problem at hand for us, so and/or graphs we have seen, you watch the video. There is another example that I have shown on matrix chain multiplication. You'll go through the video next before you come to class tomorrow, and I will discuss this quickly next day. But what is our problem? Our problem at hand is that given a definition of this, so given a definition of a state space model, where you are given the state definition, you are given the state transformation rules, you are given the start state, you are given a goal definition, and obviously you are not going to store the whole state space. So what are the methods by which you would like to find a path from start to goal, assuming all are odd nodes? And that is our first objective. And how would we define the basic algorithms? How would we incorporate domain specific knowledge? These are the things that we are interested in doing. We'll take questions now. Somebody had questions, so I would like to take questions first and then see. Yeah.
So I had a question. So in the previous, in the traveling salesman problem, you said that we have to store the exact sequence in which we are visiting the nodes. But is that necessary? Won't a set be a better way to store them? And if you know the last visitor node?
Now, if you visited and buy the set, then how would you know when you've started at A and you're at D? How would you know which way you have come?
Do we need the exact path we have used in order to find the minimum path in the end? Or will the number of knowing just the nodes which have been visited be sufficient along with knowing the last node which has been?
That's a very good question you have asked. Let me elaborate to others to explain to them your point of view. Wait. I think this is a good question you have asked, and let me try and elaborate this to others. So this is very critical about state space modeling. So please listen to what this is Neha, right? Who asked this?
Yes,
Did you ask it, Neha?
Yes, sir.
Yeah. So instead of developing a sequence, Neha says, and correct me if I'm wrong, Neha, your state definition, alternative state definition is, I keep the start S, I keep the set of intermediate nodes, this I keep as a set, no sequence. And I keep the current tip node, and I keep the cost C. Is that what you're saying?
Yes, sir. Yes, sir.
Can anybody tell me what is the advantage or disadvantage of this compared to this?
So it will reduce the state space, right? Because now we'll just need since it's a set, it can just be 2 to the power n instead.
Correct. It will reduce the state space. And firstly, the size of the state space will significantly reduce. Another advantage you will have. What does this mean? When you do this, what does this mean? This means that how does this definition D1 relate to definition D2?
So, hello.
Yes.
Why will the state space reduce? Because the cost will be different for each path, right?
Yes. So there is that you're almost at the point. The cost will be different from each path for each path. But are we interested in all the different costs, or are we interested in the?
But we will still have to. I mean, yeah. If you take a single path, okay.
Like, sir,
are we
think
interested in different costs, or are we interested in the
route? you need the root that is defined before.
No. Here in D2, in this D2, if I have two paths like this, which go through the same set of intermediate nodes I1 and I2, D2 will store two states with two different costs. But D1 will store only one state here. With which cost, Neha?
So it will be the minimum cost for that.
The smaller of the two. It will store the one which is smaller of the two. Therefore, what is a tree-like structure in D2? Those nodes will converge to a graph-like structure in D1, isn't it?
Yes.
Can you elaborate D1?
D1, have you understood D1 or not understood D1?
Not understood, sir.
Okay. So what did we define this state as? A sequence. Did you understand this? This?
Yes, sir. I have understood D2 and that structure.
Yeah, but you have not understood D1.
Yes, sir. Please elaborate with this example.
So Neha, can you tell him what is D1 here? So D1, if you have got A, B, C, D, and you have got A, C, B, D, this is in D2 are two different states, right, Prathamesh?
Yes, sir.
In D1, it will be one state. It will be defined as A, the set BC in whatever order, and tip D.
So, but we'll get to know the minimum after we have actually taken an action. I mean, when you're about to take an action, you will see which cost I'm going to take, and I'll take the minimum, right?
Yeah. So once you have got the cost, you will have to check whether such a state exists. So that this we will take care of in the search algorithm.
Yes. So when I'm using D2 also, my actual graph means that will develop, the state space that will develop when I run the algorithm will also be the same as D1.
If you intelligently create D2 and implement D2 intelligently and make sure that you identify what are known as identical paths, identical subproblems, you are right. That is exactly what will happen.
No, I'm just trying to say that only the implicit graph of D2 will be much larger than D1. But
yes, explicitly, if you implement D2 intelligently, you will get whatever D1 will get.
Okay. Yeah. Fine.
Exactly.
Sir,
You're right. You're right.
Sir, as far as I understand that some cases in D2 are repeating, and that is what is addressed in D1.
Yes, but as Ritaban has said, that the implicit state spaces look different, but when we run our search algorithm intelligently, we will take care to make sure that when D2 runs, when we come to the algorithms, you will see, we will ensure that we will not duplicate them. We will solve it just like D1. But you're right, Soma. Good. Anything else?
Excuse me, sir.
Yes.
So what is the meaning of explicit or implicit here? I don't get it.
The implicit graph is created by the state transformation rules. The state transformation rules creates a graph. Correct?
Yes, sir.
Or no? Now, in D2, the state transformation graph of D2 will be different from that of D1. That is also clear to you. The implicit graphs will be different.
Yes, sir.
Now, what is the search algorithm? The search algorithm does not store the implicit graph. We all know that in some cases it may be larger than any memory you can define in this whole world ever. Correct? So you are going to slowly make the graph explicit by starting with the start node, and you are going to slowly examine and explore the implicit graph by looking at portions of the implicit graph. Whatever you generate from the implicit graph explicitly during your exploration by the algorithm is known as the explicit graph.
Means when I'm moving through the implicit graph intelligently to optimize, reduce this.
Exactly. And we'll see those algorithms.
Excuse me, sir. So there is some like doubt that if we just give like B and C in the set in D1 state, sir, then there is a doubt that it may have been repeated, a city may have been repeated. But in D2, we actually have the configuration that a city has not been repeated and it is in the perfect order. Which are the constraints given?
Very good point. Neha, back to you. Neha, have you heard what he said?
So that will depend on how we are doing the transitions, right? While transitioning, we can make sure we don't visit the city twice.
So that is the rule of the problem, right? We're not supposed to visit the city twice.
Right,
so we will not find any states where the city is repeated.
Yes, but his question is valid that if you do a set definition, you must take care that in the state transformation rule, the set element of the set is also not repeated. That is his question. So his doubt is clear and we know the answer also. Is that okay? Who asked this question?
Sir, me, Chiragu.
Yeah. So are you clear now that you're right? You're right. But when we generate the state space, we will make sure that the children that are generated neither are part of the start, neither are part of the tip, nor are part of the set intermediate set. Okay, Chirag?
Yes, sir. Thank you, sir.
Good.
Hello.
Yes.
Sir, in case of D1, the number of states that we are storing in the state space is getting decreased, but the total number of possibilities we are checking will still remain the same, no, sir?
Very good point.
Yes, sir, exactly. It's not going to provide us with any useful advantage because in order to calculate that minimum cost, we still have to go through all the states.
No. So look at this part. Look at this part a little carefully.
Sir, maybe we are decreasing the number of states that we are considering, but the total number of iterations will remain same, no, sir?
How do we know? Let us look at this part. Let us look at this part which I have marked in red, that red box. You can see the red box now.
Yes, sir.
So now in the red box in D2, if I come through this path, then what I do from here, and if I come through this path, what I do from here, I don't want, because these two will be identical. In D2, if I come through I1 and then move on, so whatever if I come through I1 or I2, whatever I do after this will be identical. The rest of the search will be identical. So either in my algorithm or in my state space definition, I want to make sure that I do not do this repeatedly.
Sir, so in this case, if we find out the minimum of I1 and I2 for the next particular nodes, we will not check again in I1 and I2, no, sir?
No, we will not.
So this is like we are finding the problem for an intermediate node, and from then like we are initiating again.
Yeah.
Okay.
Good. My request is you all watch the videos carefully and come, and then we will discuss further. But still, if anybody has a doubt, Kshitij, you had a doubt?
Yes, sir. So my doubt is that the D1 representation means I am a bit confused about how are we defining our goal here. Like
our goal is defined as that from S, I, and T, I must cover every city exactly once, and my goal must be like this.
Yes, sir.
My goal must be A, and this is all the rest.
So, sir, my doubt is that the state space representation should be such that it should encompass all the configurations that we go through, including the initial and the final, right?
Yes.
So, sir, in the D1, in the D1 representation, where we are preferring a set over a sequence, we are foregoing the advantage of the ordering. So,
No, there is no advantage of the ordering if you are maintaining the minimum cost. All you need to know, and we shall see that in the search algorithm, is let me come back and use another color to. When you are here, can you see where I'm darkening this part? Wait, it is not coming yet.
So now I can.
Have you seen? Wait. Have you seen this darkened part in purple?
Yes, sir.
All I have to remember here is whether this came from I1 or I2. If I remember that, I will remember it.
Yes, sir. But sir, like there can be like intermediate, like here we are assuming that there is just I1 and I2. So there could be an I3 which is a cross, and like there is a cross between both the two nodes. So like there is more than one path.
Yeah, there could be other paths that will not be the same node because the intermediate sets will not be the same. Then we will create another node. The node that deeply colored node is not the node in that graph on the left. When we do it in more details, we'll see. For example, here in this sequence here, some nodes are identical. Okay, I don't see if I have made any identical. No, here no nodes are identical, but in this case, at the leaf level, at the last level, all nodes at this last level, you see that this point is same, this point is same, and this set covers this set is all same. Got it?
Yes, means in D2 it will be saved as just one set with the minimum value.
Yes,
so,
exactly.
So my doubt arises here that now if I want to backtrack my solution, I'll have to run
Yeah,
the
so
search again.
you will when you find the solution, you will maintain from where you got it. It is not difficult at all because you have got solutions. You have got, this is your final solution, right?
Right, sir.
This cost is C. Okay.
Yes,
Then from this one, and this one, once you know which, so whenever you have come here, you have got this C because this came from this side or this side or this side. You maintain the minimum, and as you have rightly pointed out, I have to remember which one was the minimum.
Yes, sir. So like my point was that we'll have to store the whole state space that we generate during the search.
No, and you don't have to store the whole state space that you generate during the search. You only store your best parent.
Okay.
Why do you need to store the others? If you come again, it has to come with some lower cost.
Right.
You only store your best parent. The others you can throw away.
Okay.
Good.
Sir, in that case, set comparisons would also make some difference, right?
Yes, set comparisons have to be done. How do you do set comparisons? How do you compare two sets?
Probably by sorting. Yeah, that is one way of doing it.
Nah. One is the simple bitmap. Nah? Two sets are equal if their bitmaps are equal. Nah? You make a bitmap of k plus 1. And then you check the first, so you have to check only the intermediate set. So you have a bitmap of all the elements. So what do you do to check a bitmap, whether they are the same or not? Which operation you will do?
Sure.
You can do any operation. All you have to say is x1 and x2 must be equal to both x1 and x2 na, after the operation, AND operation or operation, whatever. All you have to do is check whether they are so you have to just check bitwise. But there are many advanced data structures. For set operations, there are many set equivalence data structures, where there are many. But obviously you have to do a set check. But the set check will be equally difficult to a sequence check. Sequence check in some cases may be little less for smaller sequences. Good point. See, good ideas are coming up. So, the whole of data structuring, the whole of state space representation, these are important. And how do we automate it is also an important issue. So thank you all. If you have any other questions, then we can answer them. Otherwise, we can stop the recording and then we'll continue tomorrow. And there are more fundamental questions which were raised in the introductory class of Professor Sudeshna Sarkar. What is intelligence? What is human intelligence? What is thinking? So please try to figure out what they mean.
The thing is, but we don't even know how humans think. So in order to define thinking for machines.
So let me ask you a question. Will it be, I'm asking you, so you said we don't even know how humans think. I'm asking you a reverse question. Will you ever know how humans think? You're trying to find out how humans think by thinking.
Yes.
So now you tell me, can you ever find out how humans think? So can a human being find out how humans think by thinking?
Sir, every brain has different capabilities. Thinking capabilities are different for everyone. So it is a hard task to find.
So at least can you tell me whether your brain can find out by your brain's capability what your brain can do?
So
It's a fundamental question.
Yes.
I think
if you want to find out what your brain can do, then who will find out? Your brain only, na?
Yes, sir.
Is it, first my question is it possible or is it a contradiction?
It is possible, I think.
It is possible, sir.
How is it possible?
Sir, there are so many theories like we can connect with universe. So if we
Baba, all is theories that you have read. I'm talking to you logically.
So I think
none of the theories you have thought through.
It is
not possible. It's not completely not possible because our brain also changes or the cells will change. So everything is not possible to exactly understand what how our brain works, but to some extent we can by critical thinking.
So no, to some extent is not the question. Can somebody is trying to figure out can my brain understand my brain fully?
Sir, someone thinking about how his brain thinks will open up a new chapter that how people think about their own brain, and it goes on like that.
You have touched upon a very fundamental issue in philosophy.
So
Yes.
we might start from like very basic, like how a child thinks, like when he is born. So like his or her basic instincts are like to react to direct problems that he is facing in his surrounding. Like if he is hungry, he will cry. If
how do you know that is how he is thinking? You can see only crying. How do you know what is really happening inside? Do you know how an ant works? That also we don't know.
Yes, like I was thinking in such a way, like because
you are assuming
he doesn't have
that
really
what you see of the child is all the variables of the child. First, if you could do that for a child, you could do that for yourself. Because at least for you, you know some of more of your internal variables. Because how you react and what is happening inside may not be the same.
Yes, so for example, so if I walk, like if I take a walk down the street and I see something, for example, like a bike or a motorcycle, so like it's somewhat it can strike in my memory an experience of my past. So like these experiences keep on like building up as we age. So basically, like if there is a child, he has no experience. So like.
How do you know he has no experience? From where did that hypothesis come to you?
Think of a person who has undergone memory loss. Like even memory is not important. Even the process of thinking does not necessarily come from memory.
No, all these are more elaborate questions. Here you have got an entity A which wants to take an input an entity A, and find out answers about A. You first think whether this system, such a system where A, who can take input about A and answer everything about A, is possible or not fundamentally.
No.
As a mathematical system.
Sir, it will be a recursive call without an end case or return case.
So it will go into the case of infinite loop.
It is not possible.
Socho, this is C. All these thinking, winking, all these first ask simple fundamental questions.
So I think that there is a particular thing called think, like it consists of different other cognitive works, cognitive components like thinking, like learning, memory, one's experience.
So tell me what is thinking. First tell me what is thinking.
Sir, it is like kind of like a combination of memory, learning.
So can you frame it in any? Can you frame it in any of the mathematical mechanisms known to you?
Logically, we cannot frame by putting it logic.
Sir, I'd like to make a point. Combination of all the inputs we have received before.
So it's a combination of all the inputs that you have received before.
Yeah, some combination of.
Okay.
Sir, more around like if like ignore the part of thinking and just believe in behavioral patterns that a person generates over time.
Right.
How about just having a record of how a person has behaved in the past for certain actions, certain situations? We can probably be able to predict what that person can do.
That is a simplified problem. I agree what you're saying, but what I don't agree is that is not thinking.
That's not